Geometry is the architecture of the cosmos, and every star, planet, and galaxy traces lines in a universal blueprint. From the orbits that keep moons in place to the spirals that crown galaxies and the ripples that shape spacetime, math is shaping reality itself. In this journey, we connect ancient geometric ideas to modern cosmology, showing how simple shapes encode gravity, expansion, and the vast cosmic web. You'll see how symmetry and curvature aren't abstract notions, but practical tools that predict what we observe in telescope images and simulations. We'll break down the math in plain language, then watch those ideas come alive on screen with visuals that make the patterns undeniable. Stick around to glimpse the hidden patterns you've been looking for in the night sky and in the maps of the universe. This isn't just theory. It's a way to see the cosmos as one elegant geometric story. The fabric of spacetime. Spacetime is a four-dimensional fabric in which the events of the universe unfold, described by a metric that tells us how distances and durations are measured. In flat, special relativistic settings, the geometry remains uncurved. In general relativity, mass and energy curve spacetime itself, so straight lines become geodesics, the paths that free bodies follow when known non-gravitational force acts. The curvature is encoded in tensors that mathematicians describe as the Riemann tensor, which tells us how nearby geodesics converge or diverge. The Einstein field equations relate the curvature to energy and momentum through the Einstein tensor. From this geometry, what we perceive as gravity emerges as the effect of spacetime telling matter how to move. A practical way to picture this is the spacetime interval ds(2), which remains invariant for all observers. In flat spacetime, ds(2) equals c(2) dt(2) plus dx(2) plus dy(2) plus dz(2). Around a spherically symmetric mass, the Schwarzschild form of the metric deforms the time and radial components, so clocks run at different rates and light paths bend. Geodesics define the trajectories of free fall, and light follows null geodesics. This geometric view explains why features like orbital precession, gravitational time dilation, and lensing arise without invoking a force field directly. The fabric thus links how clocks tick to how space is curved around matter. Gravitational lensing acts as a natural telescope. Masses warp spacetime so that multiple images of background sources appear, and the amount of bending maps the curvature. Weak lensing across the sky reveals the distribution of matter, including dark matter, through subtle distortions in galaxy shapes. Gravitational redshift tells us that clocks deeper in a potential well tick slower relative to distant observers. Global navigation satellites rely on general relativistic corrections to keep timekeeping and positioning accurate. These observable effects demonstrate that geometry, not just mass, orchestrates the motion of light and matter. On large scales, spacetime is modeled by metrics that describe cosmological expansion, with a scale factor and a curvature parameter shaping the geometry of the universe. The Friedman, Lemaitre, Robertson, Walker framework captures a homogeneous, isotropic cosmos where expansion reshapes distances over time. The cosmological constant or dark energy component enters as a driver of the large-scale curvature, influencing how the universe evolves. Solving Einstein's equations in realistic settings often requires numerical methods and perturbative techniques to capture structure formation and gravitational waves. The geometry also imposes causal structure. Events influence only those within their light cones, which constrains information flow and horizons in surprising ways. This is the practical geometry behind cosmic evolution, the stage where matter, radiation, and spacetime itself participate in a dynamic dance. Symmetry as the language of nature. Symmetry underpins how nature fashions patterns across scales. It is the invariance of a system under a transformation that lets the same rules apply again. When a system remains unchanged by rotating, translating through space, or altering the direction of time, the laws that describe it stay consistent. That simple idea becomes a powerful guide for predicting behavior, from the tiniest particle to the shape of the cosmos. Space translation symmetry ties directly to momentum conservation, while rotational symmetry ties to angular momentum conservation. In the cosmos, symmetry is often pressed into service as a simplifying assumption. The large-scale universe is modeled as if it is the same everywhere and in every direction, an idea known as isotropy and homogeneity. This cosmological principle guides the geometry of spacetime and makes equations tractable. Observations such as the uniformity seen in a broad swath of cosmic background radiation support the notion that the universe behaves similarly across vast stretches, even though local structures break that uniformity in delightful and complex ways. At the level of fundamental physics, symmetry takes the shape of gauge invariance, where changing internal variables without touching measurable quantities leaves the equations unchanged. Maxwell's equations reflect an underlying U1 symmetry, while the Standard Model rests on larger gauge symmetries that organize particles and forces into a coherent whole. General relativity adds another layer, with the fabric of spacetime described in a way that remains indifferent to arbitrary coordinate choices, a principle known as diffeomorphism invariance. Symmetry breaking is where patterns gain texture and variety. The universe can begin with higher symmetry and then settle into a state where certain directions or properties are singled out, producing new phenomena. The Higgs mechanism is the celebrated example in which a field selects a state that gives mass to gauge bosons, altering how forces operate. In cosmology, phase-like transitions can lead to the emergence of structure as symmetry fractures into distinct configurations. Crystalline materials illuminate these ideas locally, where atomic lattices enforce precise translational and rotational symmetries, and yet defects, boundaries, or different growth conditions reveal how symmetry can be locally imperfect and still productive. Even in aperiodic structures, symmetry expresses itself through order without perfect repetition, challenging simple notions of pattern yet obeying deep geometric rules. The practical power of symmetry extends into how we design experiments and interpret data. Noether's insight that continuous symmetries yield conservation laws helps physicists organize what can be measured and what must hold steady under transformations. In astronomy and particle physics, recognizing invariances reduces the complexity of models and clarifies which predictions are robust under change. In the laboratory, symmetry guides how detectors are built and how signals are analyzed, ensuring that what is observed reflects genuine physical processes rather than artifacts of perspective. Across chemistry, condensed matter, and cosmology, symmetry serves as a language that translates geometric structure into measurable behavior, linking patterns in equations to the textures we see in the universe. Curvature and the shape of the cosmos. In modern cosmology, the large-scale shape of the universe is encoded in the curvature of spatial slices that evolve with time. The sign of that curvature yields three geometric possibilities. Mathematically, the three options are represented by a parameter k that can be -1, 0, or +1, corresponding to open, flat, and closed geometries respectively. Distances and angles then reflect this curvature. In a flat universe, parallel lines stay parallel, and the area of a circle grows as pi r²2. In a closed universe, lines can reconverge and a two-dimensional surface resembles a sphere. In an open universe, they diverge and the surface resembles a saddle. Curvature links to the energy budget through the critical density. The ratio of actual density to this critical density is captured by omega parameters, and there's some tells us about omega_k, the curvature contribution to the overall dynamics. Observable fingerprints of curvature live in distances and the way light travels through expanding space. The key idea is that curvature affects how a given physical ruler maps to an angular size on the sky, and how bright an object appears at a given redshift. Standard rulers are used to test that. The cosmic microwave background provides a pristine banner, with the angular position of the first acoustic peak, around multipole L, is almost equal to 220, encoding the angular size of the sound horizon at recombination, which is sensitive to the geometry. BAO measurements from galaxies serve as a complementary ruler. Together, these distances constrain omega_k, and therefore the curvature sign and magnitude, while accommodating the universe's expansion history and the dark energy content. Geometry is not the same as topology. A flat geometry can hide rich global topology, such as a torus where light could, in principle, wrap around and create repeated patterns, even though locally space looks flat. A closed geometry is finite in volume. An open geometry is typically infinite in extent, with negative curvature giving saddle-shaped spatial slices. Cosmic topology searches look for matching circles in the CMB or repeated patterns in the distribution of galaxies. Current data favor a universe that is extremely close to flat, with omega_k consistent with 0 within small margins, though the exact boundaries depend on the data combination and modeling. Future surveys will tighten these constraints. Even a tiny deviation from flatness can shift distance, redshift relations enough to affect cosmological inferences about dark energy, inflation, and the ultimate fate of cosmic expansion. Understanding curvature therefore matters for how we picture the cosmos outline and its long-distance connections. The cosmic web and geometric networks. Galaxies are not scattered randomly. They align along a vast network of filaments that threads through the cosmos. This arrangement forms what scientists call the cosmic web, with dense nodes where galaxy clusters sit and expansive voids filling the gaps. The architecture is sculpted by gravity acting on dark matter, guiding ordinary matter into filamentary highways and shaping the routes along which galaxies grow. From a geometric perspective, the web is a graph embedded in three-dimensional space, where nodes mark massive halos and edges trace the filaments that connect them. Computational geometry offers tools to construct these skeletons from point samples, using techniques like Voronoi tessellations and Delaunay triangulations to approximate the density field. The resulting networks reveal branching patterns, varying connectivity, and characteristic scales of alignment, serving as practical representations rather than perfect maps. Observationally, large galaxy surveys map the web in 3 dimensions, showing how galaxies cluster along long ribbons that stretch between nodes. Simulations that combine gravity with hydrodynamics reproduce the same network, validating the idea that filamentary flows feed growth of halos and fuel star formation. The Sloan Digital Sky Survey mapped the distribution of galaxies and revealed prominent filamentary structures, illustrating how the cosmic web organizes matter on the largest scales. Topological methods such as disperse, spine web, and related algorithms extract filaments by identifying ridges and persistent features in the density field. Beyond maps, the geometry of the web informs theories of structure formation and matter distribution. Filaments guide the accretion of gas and dark matter into clusters, influencing galaxy morphologies and the distribution of baryons in the circumgalactic medium. Geometric and topological descriptors, including Minkowski functionals and Betti numbers, quantify the network's shape and connectivity, helping compare simulations with observations. The interplay between topology and dynamics shows up in percolation analyses, where increasing density thresholds reveal how a single connected skeleton emerges from smaller fragments. Geometry across scales, from quantum to cosmic. At the smallest scales, geometry is not a smooth stage, but a frothing tapestry where energy and momentum can bob and weave the very fabric of spacetime. The idea of a continuous arena begins to blur. Loop quantum gravity proposes that areas and volumes come in finite units, yielding a discrete geometry described by spin networks. This is a radical shift from the familiar continuum. The Planck scale marks a regime where quantum effects of gravity are expected to dominate, inviting models where geometry behaves like a quantum lattice rather than a smooth sheet. These ideas guide how we think about gravity at the smallest scales. As we step up in scale, semi-classical gravity treats spacetime as a curved stage shaped by energy, while quantum fields dance on that stage. Light follows geodesics. Gravitational lensing reveals how mass maps into geometry, bending light to produce multiple images, arcs, and rings that encode the unseen distribution of matter. Einstein rings are vivid demonstrations. Precise measurements of lensing from galaxies to clusters enable constraints on dark matter profiles and the geometry of spacetime along the light path. Time delays in variable sources test gravitational geometry. On cosmological scales, the geometry is tied to the expansion history through the Friedmann, Lemaitre, Robertson, Walker framework, which assumes a homogeneous and isotropic universe. Curvature affects paths across the cosmos. The curvature parameter determines whether parallel lines converge, diverge, or remain parallel over vast distances, and current observations indicate a universe that is nearly spatially flat. Cosmic surveys quantify this with standard rulers. The cosmic microwave background carries subtle imprints of geometry as temperature fluctuations that map the primordial density field, while baryon acoustic oscillations provide a ruler imprinted by early acoustic waves. Gravitational lensing by large-scale structure further reveals the three-dimensional geometry of the cosmic web. Across scales, ideas from holography offer a framework in which higher-dimensional geometry might be encoded on a lower-dimensional boundary, hinting at unity between quantum and gravitational descriptions. Such ideas guide how we connect micro and macro. In practice, the geometry of the universe manifests in a web of correlations. The distribution of galaxies, the anisotropies of the CMB, and the spectrum of gravitational waves all speak to the same underlying geometric rules. The connections are not merely aesthetic. The study of geometry across scales continues with simulations that stitch quantum gravity ideas into large-scale structure, and with observations that test whether the fabric of spacetime stretches and wrinkles in predictable ways. The cosmos remains a vast laboratory for exploring how shape and scale entwine. Mathematical constants and cosmic proportions. Pi, the ratio of a circle's circumference to its diameter, roots geometry in every description of space, whether flat or curved. In cosmology, it helps convert angular scales on the sky into physical distances. The cosmic microwave background's angular features, the acoustic peaks, emerge from processes in the photon-baryon fluid and are read through spherical harmonics, where pi and related trigonometric relationships organize the math. The characteristic angular scale of the first peak is about 1 degree, a signature that geometry leaves on the afterglow. The base of natural growth, E, shows up as the exponential expansion of space when energy density stays nearly constant, as in de Sitter-like phases. That exponential form fixes distances over billions of years. In practical cosmology, solving the Friedmann equations reveals a scale factor, T, that transitions through matter-dominated power laws to periods of near-exponential growth, shaping how we map ages to distances. The math matters. Dimensionless constants, such as the fine-structure constant alpha, govern atomic spectra, and thus the fingerprints of light traveling across the expanding universe. Tiny changes would show up as shifts in spectral lines. Measurements of distant absorption lines constrain any variation of alpha to very small levels over billions of years. Otherwise, the cosmic chronometers and the fine structure of atoms would drift. The constraints are tight. Cosmic proportions are encoded in omega parameters, which compare each component's density to the critical density ρ_c equals 3h⁻2/8 pi g, yielding a clean, dimensionless set that sums to unity in a flat cosmos. That is the geometry census. Observations place matter around 1/3 and dark energy around 2/3, with the curvature parameter omega_k consistent with 0 within uncertainties, marking a universe that is very nearly flat. Baryons make up a few percent of the critical density, while cold dark matter accounts for about a quarter. The interplay of these proportions is visible in the cosmic microwave background's acoustic peaks and in baryon acoustic oscillations, which encode a standard ruler that ties distance scales to redshift and thus to the universe's expansion history. These features rely on constants and proportions working together. By fitting CMB data, galaxy surveys, and supernova distances, cosmologists infer the same set of omega values and check consistency across probes, testing the overall geometry and the matter-energy budget. Even small deviations would prompt revisions. From geometry to dynamics, predictions, and observations. The geometry of spacetime is not a backdrop, but a dynamic stage on which matter and light trace their paths, bending, stretching, and accelerating under gravity. Mass energy tells spacetime how to curve. From this curvature, predictions emerge about how galaxies move, how photons travel across vast distances, and how the universe itself expands or contracts. These are dynamical consequences of geometry. Geodesics trace the natural routes for freely falling matter and light, linking the shape of the cosmos to the tracks we observe in skies and surveys. Einstein's field equations connect the curvature of spacetime directly to the energy content, turning geometry into a driver of cosmic dynamics. The FLRW model assumes uniformity on large scales. Solving those equations with the observed mix of matter, radiation, and dark energy yields a history of expansion and a prediction for how structure grows from tiny fluctuations. Spatial curvature affects the apparent size of distant objects and the pattern of fluctuations in the cosmic background. Gravitational lensing magnifies and distorts images, offering a map of mass that itself reflects both geometry and dynamics. The cosmic microwave background carries the imprint of geometry at the moment photons decoupled, and its acoustic peaks lock the overall curvature and expansion history. Weak lensing surveys measure how light is sheared by intervening mass, revealing how structure has grown over time. Baryon acoustic oscillations in galaxy surveys provide a standard ruler to track distances and the expansion rate as the universe evolves. Gravitational waves reveal dynamical spacetime through actual spacetime ripples emitted by merging compact objects, a direct test of Einstein's geometry in the strong field regime. Together, these observations knit a coherent picture in which geometry dictates dynamics, and dynamics in turn reveals geometry. Analyses must untangle degeneracies among curvature, dark energy, and matter density, because several different parameter combinations can produce similar distance measures. Combining probes, the CMB, lensing, BAO, standard candles, and gravitational waves, reduces ambiguity and tightens constraints on the cosmic geometry. Current tensions, such as differing measurements of the expansion rate from early and late-time data, fuel debates about potential new physics. Upcoming surveys and missions promise sharper maps of geometry and a clearer view of how dynamics emerged from it. Euclid, the Rubin Observatory, and LISA will probe geometry and growth across cosmic time, testing whether general relativity holds on the largest scales. Across this journey, we've seen that the cosmos is written in geometry. Space-time itself curves, light travels along those curves, and gravity sculpts a vast cosmic web that binds galaxies into a grand lattice. The patterns show up in the cosmic microwave background, in how matter clusters, and in the way symmetry and scale let simple laws blossom into astonishing structure. From curved space-time to the shimmering networks of galaxies, the math is a language that helps us make sense of what we observe. If you watched and felt that sense of awe, you're not alone. These ideas invite us to pause, look up, and imagine the quiet rules at work behind what we see. When you gaze at the night sky or study a map of the universe, you're already engaging with the same geometric logic. If this exploration resonated with you, consider subscribing, tapping the bell, and leaving a comment about the pattern that spoke to you most, the one you tend to notice in data, maps, or the sky. A like helps others find this kind of curiosity too. Looking ahead, we'll dive deeper into how dark matter threads the cosmic web, what gravitational waves reveal about geometry and motion, and how simulations turn equations into living pictures of spacetime. There'll be more visuals, more connections, and chances to explore the geometry of the cosmos together. Until next time, keep spotting the geometry around you. The universe hides its patterns everywhere, and the more you look, the more you'll see.